Very good morning to all. It is our great pleasure to welcome you all again to the Knowledge 4.0 webinar series. Chennai Technology has been taking a great initiative to enhance the knowledge of faculty, researchers, students through the Knowledge 4.0 webinar series, which is one of the unique and distinct initiative of Chennai Technology. This initiative is being successful in different scenario by the motivation and support from the management, especially from our chairman, Mr. C. Priram, Mr. Honorable P. Sriram. Chennai Technology has been conducting webinars in different scenarios such as technical webinar series, research webinar series, career guidance webinar series, and innovative webinar series, and alumni webinar series. Along this webinar series, we are also conducting national and international seminars, national and international workshops, faculty development programs, and lecture series. Today, we have two qualified researchers, Mr. Dr.G.Udaya Kumar, from postdoctoral fellow from Kookmin University, who is going to talk about the research scopes in pool boiling. I welcome you, sir, for this wonderful forum.
Thank you, sir.
And later, Dr.R.Ajith Krishnan, postdoctoral researcher from Kookmin University, is going to join with us, and who is going to deliver his lecture on research scopes in flow boiling. So it is my great pleasure to welcome Dr. Ajith Krishnan to this wonderful forum. I welcome Dr. Ajith Krishnan, sir. And Chennai Institute of Technology was established in the year 2010 by our Honorable Chairman, Sri P. Sriram. Today, our institute is being within top 10 among all other private engineering colleges in Tamil Nadu. This webinar series has been purely initiated in order to enhance the knowledge of faculty, researchers, and students community as a social responsibility. Chennai Institute of Technology is keeping the motto, the lockdown is only for the nation and worldwide, but there is no lockdown for learning. By keeping this as motto, Chennai Institute of Technology has been taking a tremendous effort in conducting this webinar series, and so far, almost 200 webinars is going to be over in next few days. So it is my great pleasure to welcome you all the participants, and I request you to get some very good idea from these two researchers, which will help you to learn the basics as well as to get into research. Now I request Ms. Swapna Sri, student of second year mechanical, to introduce our today expert member, Dr. G.Udaya Kumar.
Thank you, sir. Good morning, everyone. Myself, Swapna Sai, pursuing second year mechanical engineering at Chennai Institute of Technology. Dr. G.Udaya Kumar, postdoctoral research fellow, Kookmin University, Seoul, South Korea. He did his BE mechanical engineering from Ponnaiah Ramajayam College of Engineering and Technology. He did his ME from Saranathan College of Engineering and obtained his PhD mechanical engineering in experimental investigation on pool boiling heat transfer enhancement of surfaces coated with graphene and metal nanowires from NIT Trichy. He is currently working on pool boiling heat transfer enhancement using laser textured surfaces and self-riveting fluids. He expertises skills in fluid mechanics, heat transfer condensation, phase change materials, bubble dynamics, and thermal management. He has published over 30 international journal articles and conference papers with high impact factors. We welcome you, sir.
Thank you.
Sir, please, you can go out with the session.
Yeah, thank you. So I would like to stress that my publication is 13 and not 30. So good morning, everyone. So here I'm going to share my screen. So hope you can see. Can you see my screen?
Yes, sir. Please open PPT. Yes, sir. Please open PPT. Sir.
Yes. So is it visible, sir?
Yes, sir. Please, you can go ahead, sir.
Yeah. So good morning, everyone. This is Dr.G.Udaya Kumar. I'm doing my postdoctoral research in Kookmin University, South Korea. So today I'll be talking about the research scope in pool boiling heat transfer. So myself combining with Dr.R.Ajith Krishnan will be giving you general idea about boiling heat transfer. I'll be talking mostly on pool boiling heat transfer, and he'll be taking sessions on flow boiling heat transfer. Now these are my research areas which I'm interested in, and also I'm doing some works in these all areas. So during my PhD I did pool boiling heat transfer using metal nanowires and carbon nanotubes. Here I'm involved with laser textured surfaces for improving the boiling heat transfer, and again some works on hydrogen energy storage using something called LOHC, liquid organic hydrogen carriers. Now I'll be talking about the pool boiling, the mechanism and the enhancement techniques, and some basic explanation about the research works in these areas and what are the future scope that we can take in this area. Boiling. So the main difference between evaporation and boiling is evaporation is a surface phenomena and boiling is a bulk phenomena. So the phase change from the solid, so from the liquid to the vapor, if it's taking place in the surface of any liquid surface, it's called evaporation. And if the same process is taking place in the bulk, is called boiling. Now there are many thermodynamic differences between them, but we are not going in that detail. Particularly talking about boiling, it can be categorized into pool boiling and flow boiling. Now, if the volume of the liquid or body of the liquid is not flowing, and if it is stationary like a swimming pool, then it's called pool boiling. And if the fluid is boiling when it is in flow, then it is called flow boiling. So I'll be talking mostly about pool boiling, where the stagnant fluid or a pool of a liquid is boiling by phase change, and it can be categorized into saturated and subcooled. Now if we consider this as a boiling surface and surrounded by a boiling fluid and which is stationary, then the temperature of the fluid as compared to the temperature of the surface varies. If this temperature of the fluid near the surface is at the same temperature as of that of saturation, it's called saturated pool boiling. At the same time, in most cases, in most practical cases, the fluid surrounding the surface will be at lesser temperature as compared to the saturation temperature. In that case, it's called subcooled flow boiling. So here you can see it clearly. Now, why pool boiling? Why we are talking about boiling here? Because in heat transfer, the amount of heat transfer or the value of heat transfer coefficient which can take place in during this phase change, let it be boiling or condensation, the value is very high. So you can see here for comparison that in as compared to natural convection or forced convection, the heat transfer coefficient value, the range of the value which it can deal with is very high. And specifically talking about pool boiling, you got no moving parts, you got very less components as compared to other techniques. That's why we are particularly interested in this concept of pool boiling for many applications like boilers, steam generators, heat exchangers, and many type of evaporators, many energy conversion systems. And the recent application is immersion cooling, where you got the electronic chip or the electronic assembly and you are immersing it into a pool of liquid. Now this is just to cool the part of electronics where the air cooling is not sufficient, and that's why it is called immersion cooling of electronics. And the main principle behind this immersion cooling is pool boiling. Now the basic trend in the pool boiling analysis started with the concept of Leidenfrost in 1756, where he gave a concept of droplet bouncing on a surface which is at very high temperature. Following him, after 200 years, it was Nukiyama who initiated the characterization of boiling using a nichrome wire, and the further works by Driven Mueller gave result into this pool boiling modern curve, which is still in use for explaining all kind of phase change processes. Now see here, this is a characteristic pool boiling curve for any surface fluid combination. Now the nature of this curve may change for different combination, but we are considering as a standard form, and we are using it to explain the nucleate boiling region. Now whenever the boiling occurs, initially it's a natural convection process and not the boiling, and there comes a point where your boiling initiates. If you take any surface, it will have lot of cavities or pores present in it. When you heat it, it will have trapped air into it, and when you are heating it, the air or the vapor, it will expand, and it will result into boiling, that is bubble generation. Boiling is nothing but bubble generation. Now that's why this is called boiling incipience or onset of nucleate boiling. This is the point where the first bubble initiates or starts to generate. Now once this bubble initiates, and as the temperature of the surface goes on increasing, you can see many different bubbles are generated on the surface. That's why this region is called isolated bubbles region, where you have number of bubbles on the surface, but they will not be interacting with each other, because still you have many gaps in between them, and that's why it's called isolated bubble region. But as the heat flux increases, as the temperature goes on increasing, the interaction between these bubbles increases. Initially it will be a vertical interaction resulting into slugs or columns of bubbles, where you have a continuous bubble generation, and after some time the horizontal interaction starts to take place, and it leads to a state called critical heat flux. Now in any pool boiling heat transfer system, or any system which is working based on the principle of pool boiling, has to be characterized with three parameters. One is boiling incipience, next is the slope of this curve. Here you have Q, that is heat flux, and here you have the del T, that is surface superheat, which is nothing but this difference between the surface temperature and the saturation temperature. Now Q, this heat flux divided by surface superheat, will give the heat transfer coefficient. Now that is nothing but the slope of this curve. So the slope of this curve is very, very, very important, and this point, which is called critical heat flux. Now as you can see, this onset of nucleate boiling and heat transfer is the performance parameter. These two parameters will give you the measure of the performance of the system, but this critical heat flux is not the performance parameter, it's the safety parameter. Now this is the critical point above which any system should not be operated or cannot be operated, because above this, burning will take place or the system failure will take place. That's why the whole research is lying on increasing this point. You have to increase, for example, the corresponding heat flux is this one, then you have to take measures or efforts to increase this critical heat flux by doing some modification. Also, if you can increase the slope of this curve, then it is advantageous. The whole research is lying in this nucleate boiling region, and this region is of very less interest or no interest, and it has got very specific application related to this, but most of the applications are involving this nucleate boiling region. That's why I have highlighted it as region of interest. Now so here I have given the pictorial representation of the individual operations or the activities taking place right from the free convection to the boiling incipients. So here you can see the initial bubbles are generated, and they are randomly generated in some very less spots. But as the heat flux increases, you can see the isolated bubble region where you have more number of bubbles initiated. Now the concept is the number of bubbles generated or the nucleation site density goes on increases with the increase in heat flux or temperature, and again as it decreases, the activation of the cavities also decreases. That's why you can see when the boiling decreases, it comes to it back to own position, the density of these bubbles decreases. Now but as when it is going forward, the horizontal or the initially the vertical coalescence of bubble takes place, and you can see the bubbles merging with each other, thus resulting into slugs. And when this condition becomes so harsh, that these vapor completely cover this surface, and there comes a layer of vapor in between the liquid and the solid surface, and this restricts the heat transfer from solid to the liquid, and that's why the temperature of the surface increases to very high value, and suddenly the surface can burn or can fail. That's why this condition is called critical heat flux. That means it's very critical, and any system should not be operated at that point or above that point. Then it comes to transition, where this transitions to film boiling region, and this transition region is very unstable, and it takes place between this nucleate boiling region and film boiling region, and that's why the heat transfer is very less in this, and that's why you can see in the pool boiling curve the slope is decreasing again. But again, when this temperature goes to very high value, in this region radiation comes into act in this film boiling region, and that's why the slope again increases, giving the very high heat transfer value. But this region cannot be operated practically, it is very difficult. That's why the practical application related to this region is very high. In nuclear field, these applications are used. Now, bubble evolution cycle, as I explained already, the initial point of the generation of the bubble is called bubble incipience point, and the whole cycle, which starts from the generation of the bubble to the growth and to the departure and to the new nucleation, this whole cycle, it is called bubble evolution cycle. So here you can see there is a cavity. So in any surface we have many cavities naturally formed, or we can form artificially. Now they will be of very different shapes and sizes, but for standardization and for ease of understanding, we have made it as a conical cavity. So here you can see a conical cavity which is having an initiation of a small embryo of bubble. As the temperature increases, it increases in the size, because inside the expansion happens, the pressure increases, and you can see that the edges of the bubbles are pinned or attached to the edges of this cavity. Now again, a condition comes where this goes beyond this edges, and suddenly a condition where it departs. Now this departing is very important for the heat transfer process, because the moment when it departs, it creates a flow in this area, which makes the liquid from top or side onwards to come and wet the surface again. Now this activity or this phenomena is very important to maintain the boiling in the surface. Now once the bubble departs, here again a nucleation of a new bubble initiates. Now during this pool boiling, there are many type of interactions between the fluid and the surface, between the bubble and the surface, bubble and the liquid. So this is a very complex phenomena to understand. And there are, again I am coming through all the definitions which we are using in this pool boiling. So as I told, the onset of nucleate boiling or boiling incipients, where the bubble starts to initiates, and this bubble incipients depend on many factors, and some of the factors are surface superheat, number of active nucleation sites, and the wettability of the fluid surface combination. Now this wettability plays a very important role. The nature of the surface, whether it is hydrophilic or hydrophobic, or superhydrophilic or superhydrophobic, this nature means this wettability in combination with the fluid used is very critical in deciding the boiling incipients, heat transfer coefficient, and critical heat flux. You can see in that in critical heat flux also this wettability plays a very important role. So in this pool boiling, just keep in mind, the more the bubble, the more the heat transfer, and the number of bubbles will be more if the departure time is less. So if you take a particular window of a time, if the departure diameter is less, it means the frequency is going to be more. So number of bubbles has to be increased, and the departure diameter has to decrease, and the frequency with which the bubble is removing or being removed from the surface should be very high to overall play a role in increasing the heat transfer as well as critical heat flux. Now again you can see that this heat transfer coefficient is depending on the wettability, the frequency, bubble departure diameter, and the nucleation site density. So all these factors play a very important role in deciding the nature of pool boiling heat transfer, or the quantity of heat transfer coefficient. Now here a small analogy for the departure, growth and release of the bubble. So there are many forces which comes into act during this action, but I am taking into example only two forces, that is buoyancy and capillary. Now the buoyancy force, which will always tend to remove the bubble away from the surface, but the capillary force will pull it always towards the surface. So the balance between these two forces plays a very important role in the bubble departure. Now if the capillary force is less as compared to the buoyancy, then the bubble is going to be removed. So that's why the force analysis in this case is very important. To analyze the critical heat flux, or many models are available. So how the critical heat flux takes place, basically it's the generation of a film above the boiling surface, a vapor film above the boiling surface, but it is still more complicated than this, and there are many models. Even now there are many models which are coming to explain the concept of critical heat flux. Now the understanding of this critical heat flux is very important to improve the characteristics. Until now the clarity is very less in this field. Now this is the mostly used Zuber correlation to calculate the critical heat flux in a given liquid fluid surface combination. Heat transfer, when, as I told, the main heat transfer is because of the bubble. Now when the bubble departs, the flow it generates behind its movement is very important, and at micro, macro, at different scales, different phenomena comes into act to improve the, or to play a role in the heat transfer. And again, important role is micro layer evaporation. So it is believed, or it is proved, that very small, very thin layer of liquid is present between the bubble and the liquid surface, which is very important in this heat transfer process, and that's why it is called micro layer evaporation. Now the mechanism, as I told you, see, you can see here what are the different heat transfer mechanism that are taking place at different scales. When the bubble is being generated, it gets growth, and during its departure. So you can see the moment of bubble here, and how the liquid from sideways and from top it comes and wets the surface and helps in the formation of a new nuclei of bubble. Now to calculate the heat flux in this nucleate boiling region, this is a famous correlation given by Rosanov. So you can see that this is a very complex correlation because it depends on many parameters, like the properties of the surface, the properties of the liquids, and also the atmospheric conditions. And that's why this is a very complex process which is taking years for a clear understanding. Now again, this is a used correlations for minimum heat flux and maximum heat flux. Now again, we are talking about enhancement in pool boiling. When we talk about enhancement, there are two types, mainly active and passive type. Now in active, you can vibrate the surface, or you can supply the liquid from external sources, or you can keep some rotating fans or mixers to improve these heat transfer convection, as well as to remove the bubbles at earlier stages. But again, if this is energy consuming, and there are some passive type of enhancement technique also. So when we are talking about passive, you have to play with the surface as well as the liquid. Now you can modify the surface. So by modifying the surface, you mean to change the wettability, change the surface roughness, change the porosity, changing the capillarity, and the design aspects of the boiling surface, as well as you can change the fluid, or you can change the operating temperature and pressure. So these are the ways by which you can improve or enhance the boiling heat transfer in different ways. Here we are mainly talking about the modifying the boiling surface. Now what do you, as I told you, you are mainly doing increasing the nucleation sites, or you are playing to modify the wettability of the surface liquid combination, and thus you are increasing the bubble heat transfer or boiling heat transfer, because the modifying the surface parameter will improve the bubble dynamics, or will modify the bubble dynamics. And this change in bubble dynamics, the way the bubble is generated and it is departed from the surface, plays a very important role in deciding the heat transfer as well as CHF. Now, there are many techniques which can be used, and during my PhD, I have taken the aspect of nanomaterial and nanostructures. So, as mentioned already during my introduction, I used metal nanowires and graphene carbon nanotube based surface modification techniques to improve the pool boiling. Now, this was a paper which was published by Professor Satish G. Khanlikar in 2019, last year, and this was a very interesting paper. And I would, whoever is interested in doing research in pool boiling heat transfer, I would like them to have a look at this paper. This was yeah, I have given the name as well as the details of this paper. You can see here they have explained the mass transfer and the liquid motion during the bubble generation and release, and the important aspect they have given, you can see in this red zone, that till now everyone is thinking that the 90% of the heat transfer is taking place in this region only, where the bubble is attached to the surface and the growth of the bubble is taking place by the energy transfer from the surface to the liquid. But in this paper, he has given an insight that the heat transfer percentage during this phase, the growth of the bubble, is only 40%, and most of the heat transfer takes place when the bubble is actually traveling away from the surface, and it is actually from the superheated liquid which is surrounding the bubble during its upward motion. So you can see the red zone here. So he's saying that there is a lot of scope for further research in this area if you can try to understand the motion of the bubble when it is moving away from the surface. That will play a major role in deciding the actual nature of boiling heat transfer. So that's why I have given here the liquid flow in the superheated bulk. This red zone is the superheated bulk zone, where you are seeing the this zone is the superheated bulk zone, where you can see that the liquid, the bubble, so this superheated zone helps in the actual growth of the bubble during its motion, and the actual heat transfer, around 50% of the heat transfer takes place here. And the micro layer concept, which I already explained to you, is still not clear, and again the behavior of this micro layer at higher heat fluxes is not explained till now. So we got a lot of research scope in these areas. Now, I'm sure that I have made something clear in the basics of the pool boiling research. Now I would like to give you the different aspects in which this research can be taken. So first is boiling surface. So people have using micro channels, micro porous coatings, nano coatings, chemical coatings, an interesting concept of re-entrant cavities, and nanotubes and nanowires, and recently laser texturing. Now see what happens during this coating and this thin film concept is the durability concept. Means no matter how efficient the coating is when you are doing the test for the first time or second time, or no matter how efficient it is, but after the number of cycles, for example 10 cycles, the coating is going to come out. So the durability is a big question, and that's why we are interested to work in this concept of laser texturing. Now what happens is, using this laser femtosecond lasers or picosecond laser, you can create structures. It can be microstructure, it can be nanostructure, or it can be hierarchical structures, where you have nanostructures over the microstructures, and you can actually mimic the properties of the coating, all the wettability or surface roughness properties, using this laser texturing. And similarly, electrochemical coatings, you can use metal meshes, and now recently 3D printer structures are coming into act. Now you have the additive manufacturing technique, using which you can do anything, but additive manufacturing of metal structures is not that much developed, which is actually required for this kind of applications. Now when it comes to the boiling fluid, see, most of the applications are using DI water, but when we are talking about electronics cooling, we cannot use water, because water is electrically conducting, so we cannot use it for the immersion of the electronic system into that. So we have to go with something called dielectric fluids, special fluids. But the problem is the thermoelectric properties of the water is the best, and you can improve the properties using adding some nanoparticle and resulting into nanofluids or other kind of fluids. But when you are going for immersion cooling, that is direct immersion, you cannot use water, and that's why you have to go with dielectric fluid. But the thermoelectric properties of dielectric fluid is very very poor, and that's why you again got lot of scope of research in that area. Now when it comes to bubble dynamics, see the bubble dynamics, how the bubble behaves is a very very big area of research, and mainly here it comes the high speed imaging and the image processing. So if any one of you is interested in the image processing, see when there are very less bubbles, the individual bubbles, or at lower heat flux, if you have lesser bubbles, you can manage it. But what will happen when the number of bubbles is too much? The coalescence of bubbles is too much that you cannot actually study the how they are behaving at higher heat flux, because there are so much of bubbles interacting with each other. You cannot actually see as individual bubble how it is behaving. So if you can come up with an idea at using which you can analyze the behavior of bubbles or the dynamics of bubbles at higher heat fluxes, it will be great. Till now there is no work in that area. Now again you can change the orientation of the whole chamber or the surface, and gravity effect, which is actually the space cooling. So this pool boiling actually is used for the space cooling of electronics in the space. So there the buoyancy force is not there. So how you are going to use this? So that is again very interesting work. And Dr. Rishiraj from IIT Patna, his research group has done lot of research work in these areas. I request you to visit his website if you want to get more information on that. Now I hope I have made myself clear in the various research scope involving boiling surface, boiling fluid, experimental condition, as well as the bubble dynamics. Now see, I want to just give an example or an insight involving the boiling surface of different kind of structures that are being used or being studied to improve the boiling heat transfer. You can see the reentrant cavities, micro channels, mini channels, and nanowire coatings, porous coatings using sintering technique, and electrodeposition based coatings. So there are, and these are just examples, and you can see number of works using this surface modification technique. And if any one of you is working in this kind of area involving coating or surface modification for some other application, it may not be necessary that it is for pool boiling, but for other application. But if the structures are interesting, if the durability or the strength between the metal surface and your coating or your surface modification is better, because I think many people will be working using the electrodeposition technique or the 3D printing or many other techniques. For it may be for any other application, but it may be possible that you can apply the same thing for this application, and I would suggest you to investigate in that aspect. Now again, boiling liquid, as I explained, there are many things, but I would like to bring you notice two important things. One is self-reverting fluid and one is ionic fluids. Now what is a self-reverting fluid is, see, generally for ordinary liquids, as you can see is in this graph, as the temperature goes on increasing, the surface tension decreases. But there is a class of fluid called self-reverting. It's nothing but aqueous alcohol solution for some only selected alcohols. When the alcohol is mixed in the water in very very low concentration, and it was observed that above a particular temperature the surface tension actually increased then decreased. So, and this was very interesting phenomena, and this phenomena was used for to improve the boiling. So what happens, because of this surface tension change, the liquid actually travels towards the surface at higher temperature. So what we need during the pool boiling heat transfer enhancement is, as the bubble moves away from the surface, the liquid surrounding it has to travel towards the surface, and it should wet the surface. It should for the next possible generation of bubble. So at higher heat fluxes this does not happen. At higher heat fluxes what happens is, you have so much bubbles, continuous bubbles, that the liquid cannot come and touch the surface. But when used with these fluids, the performance was found to be improved, but this has got some safety issues associated with it. There are fuming of the particles, and the particles are actually very much moving in the air. So that's why it has got many chemical aspect related problems. So if any one of you can address that point, it will be very interesting. And recently, ionic fluids, these are a special class of fluids. These ionic fluids are actually used in the only for chemical application. But again, Dr. Ishiraj from IIT Patna, he has utilized these ionic liquids for pool boiling heat transfer and also for space electronics cooling, and the results were amazing. So you can see that using water, the bubble size is very big. That means you can't see the individual bubbles. But when you are using this surfactant added and again the ionic liquids, you can see the size of the bubbles are decreasing. That means the individuality of the bubbles you can see here, there are many small bubbles. So what happens when the bubbles are made smaller is the heat transfer increases and the coalescence also decreases. So this actually improves both the heat transfer as well as the CHF. Now let's go to the specific applications of electronics cooling. Time
Fine. So,
Hello sir, are you there?
Sir, tell me, sir.
Can you tell how much time I have left?
So you can take your own time, sir. Your comfortable
Okay,
time.
fine. So now we are moving for the electronics cooling. Now here we can see that as the number of processor increases, the heat generation increases. And now the condition is going beyond the Moore's law. That's why it's more than Moore. And we are using a lot different kinds of liquids for this immersion cooling application. Water cannot be used, so there are different kinds of liquids which can be used for this application. You can see here when you are talking about electronics cooling, it can be passive or active. And in passive, it's mainly electronic, it's air cooling, and active, it can be liquid or air. When talking specifically about liquid cooling, you can see here it can be indirect liquid or direct. In direct also it can be single phase or double phase, and immersion can be single phase or double phase. Now we are here working with the something related to immersion two phase cooling, that is pool boiling. Now, the main principle behind the immersion cooling is nothing but the pool boiling heat transfer. And that's why we are studying the basics about the pool boiling, how it behaves with this kind of fluids. And there are many companies which are actually involved with this immersion cooling concept. Now, these are some articles to prove that they are actually in the market, they are actually in applications. Now, here, as I know that I have mentioned previously the role of wettability of surface in deciding the pool boiling. So we should know what is this wettability. Now the interaction between the liquid and the surface will decide the wetting nature. If the liquid spreads evenly on the surface, it's called wetting. If it forms a droplet on a surface, it's called non-wetting. And if it is between in these two conditions, it's called partially wetting. So the interaction of energy, the surface energy and surface tension, the balance of these two energies plays a major role in deciding the wettability. Now, what is contact angle? If you take a droplet on a surface, an ideal condition where the surface is homogeneously smooth, homogeneous in terms of chemical composition. So it's an ideal condition that we are assuming that the whole surface is made up of only one kind of chemical and it is perfectly smooth. In that condition, the angle subtended at this 3-point contact line, it is called three-phase contact line, where you can see all the three phases merging together, and the angle subtended through the denser medium, through the liquid. It is not the angle at opposite, it's always the contact angle should be measured along the denser medium. So the force balance between these three phases at the three-phase contact line and the angle subtended through the denser medium is called contact angle. Now again, it is just to show the balance between different forces. If this contact line is less than 90 degree, it is called hydrophilic. If it is greater than 90 degree, it is called hydrophobic. If the angle is very less and the liquid just spreads on the surface, that is, if it is less than 30 degree or even 20 degree, it is called super hydrophilic. And if it forms a droplet on the surface and if it is rolling like a water on a lotus leaf, it is called super hydrophobic. But the contact angle concept in terms of bubble is totally opposite. So as I mentioned, the contact angle should be always measured through the denser medium. In case of bubble, the naming becomes difficult. That means bubble in a hydrophilic surface actually looks like a hydrophobic droplet. So you have to be very careful when you are describing the contact angle related to droplet as well as bubble. But usually for convection, the contact angle wherever it's measured, it will be taken with respect to the droplet on the surface only. And this analogy using the bubble is seldom used or very less used. Now this is a Young's equation, which is giving the equation for measuring the contact angle on ideal homogeneously smooth surface. And we are moving towards a Wenzel and Cassie-Baxter state, where you can see no surface can be homogeneously smooth. So here we are assuming the practical case of rough surface. So this is the equation which is actually taken for involving the roughness of the surface. So here you can see that this equation is very, very important because here we are assuming the homogeneous surface, but it is with having some roughness. So if you are having a hydrophilic surface and if you are giving any roughness, then you will find that the surface will become super hydrophilic. At the same time, if you have a hydrophobic surface and if you are generating some roughness on it, it will in turn become hydrophobic. That means the contact angle will increase in that case. So that is the importance of this surface roughness value here. And whatever the coating or the surface modification we are doing is nothing but we are just playing with the roughness parameter here, and we are changing the wettability of the surface. Now again, the representation of the roughness factor. And Cassie-Baxter, if you are removing the concept of roughness and only bringing the heterogeneous concept of chemical composition, if you have two surfaces involved, then the resultant equation will be something like this, which will be combination of the role played by all the solid fraction values. This is the Cassie droplet state. It's actually the representation of the droplet on lotus leaf, how it will look or how it will be. The droplet will be actually hanging on a surface, on a rough surface filled with air. So you can see here in all these roughened surfaces, in the gaps there will be air. This air will be actually working as a second surface. So thus the equation becoming in this way. So this is called Cassie droplet. Whenever you are measuring contact angle or wettability of any surface, it cannot be measured only with the contact angle. Contact angle is sometimes is not the complete output, complete result. So we have to mention something called advancing contact angle and receding contact angle. So whenever you are measuring the advancing contact angle, you have to increase the droplet amount during the measurement. I hope whoever is involved in this kind of research, they'll be knowing well about this advancing and receding contact angle. I'll try to explain it using this. So if there is a droplet which is sliding on an inclined surface, you can see that the front edge will be having the higher angle as compared to the back edge. So this analogy we can use, and the difference in this angle is called contact angle hysteresis. So if you want to make a super hydrophobic surface, then the contact angle has to be higher than 150 degree. At the same time, the contact angle hysteresis should be very, very low. It should be less than the 5 degree or 10 degree. Only in that case the droplet will actually roll. So what will happen if you take a rose leaf? Even in that rose leaf, you can see that the droplet is having very high contact angle. But even if you invert the rose leaf, you can see that the droplet is actually hanging there. It will not fall. But in lotus leaf, if you take the lotus leaf, the droplet, it will be actually dancing on the surface. It means that it will easily move. So this is a difference example to explain the concept of this contact angle hysteresis to you. Now I hope I have explained you the basics of wettability, and now we are moving to the my experimental setup to study the pool boiling. So this is my initial representation of the pool boiling experimental setup, where you can see the boiling chamber, the boiling surface, and to boil you have to give actually the heat input. So we have the heat input system, and when the to maintain the saturated condition, already I explained in the second slide that saturated temperature boiling is where the surrounding liquid is also at saturated condition. To maintain this, we have to use an external heater or an extra heater to maintain the water at saturated condition, and that's why it is called secondary heater or auxiliary heater. Then when the vapor is formed, it has to be condensed, otherwise it will escape, or inside the pressure is going to increase a lot. So that's why you have to keep a condenser also to condense the evaporated liquid, which will be fall off, and this is also to maintain the pressure and the level of liquid inside the chamber. Now you have a data logger and chiller, and always the controller to control the operation of the auxiliary heater. Now here is the view of the boiling chamber and the heater arrangement. This is the diagrams. You can see the individual elements here: the heater, the heatsink valve, and the Teflon cover we are using for the insulation, the power supply, the high-speed camera, the condenser arrangement, everything. This is the photograph of our pool boiling heat transfer experimental setup. You can see the boiling chamber along with the high-speed camera, all these arrangements. Now, when you saw that the pool boiling heat transfer is all about measuring the heat flux and the temperature value, the delta surface superheat value. Now the methodology to calculate these two values are given here. Now I don't want to go into these aspects. Now you can see I have done the repeatability test, the heat loss test, uncertainty analysis, and we have used the FC72 dielectric fluid to be act as a immersion cooling liquid. You can see the basic properties. The boiling point is only 56 degree as compared to the water. You can see the comparison here of water and this FC72. So you can see the thermal conductivity value and latent heat of vaporization. It's very low for this FC72. You can see that the latent heat of vaporization is only 95 as compared to the 2000 of water. So it's very less. As also you can see the specific heat of FC72. So during this deficiency in thermoelectrical properties, we have to do lot of other ways to enhance the pool boiling performance when you are using these kind of liquids. Now the dielectric properties, here it is better as compared to water. Now these are the main objective or why we are using the enhancement technique, because when you are using this FC72, it will completely fill the cavity and you got no vapor. There is no vapor actually to because this FC72 is highly wetting in nature. It's highly wetting because surface tension is very low. So that's why this will completely flood the whatever the available cavities are there. So that's why you have to give some extra provision for the nucleation, and that's where the solution comes as metal nanowires and carbon nanotubes. So we have given some surface coating which will give you some extra nucleation sites. Now initially we have used carbon nanotube. So what is the basic principle behind this carbon nanotube growth I have shown here. Now we have used CVD technique, PECVD technique, plasma enhanced CVD technique, to grow the vertically aligned carbon nanotube over the copper substrate, and in between we have used the graphene intermediate layer. So this graphene also we have grown using the CVD technique only. This is a mechanism of CNT growth in any metal surface. Now this is the graphene we have actually grown over copper. This is just for illustration here, the experimental conditions for growing the graphene over the copper substrate. These are the basic results. We did only with graphene without any other thing, and we got very similar performance as compared to that of water. So this is the representation for all the mechanism of CNT growth over copper. Basic characterization. This is the same image. You can see the CNT and the FLG layer over the copper substrate here. AFM analysis. This is the pool boiling heat transfer curve. So you can see that when we have used this graphene CNT heterogeneous combination as a pool boiling surface, the performance increased very high. You can see the CHF as well as heat transfer coefficient increased a lot as compared to plain surface as well as only graphene coated surface. This is heat transfer coefficient. Again, the heat transfer coefficient also increased as compared to the other two surfaces. This is the basic boiling dynamics. You can see the bubble dynamics here. Now it is taken with different temperature value and heat flux values for different surfaces, and you can see that in case of the graphene coated or graphene carbon nanotube coated surface, the number of bubbles is high as compared to the other two surfaces, as well as during the higher heat flux the individuality of the bubbles is maintained even at very high temperature. Again, the basic bubble dynamic analysis. And this is the physical mechanism. So what happens to the liquid penetration and how the cavities are actually saved from flooding during this coating, using this coating. Basic conclusion. And then we have used the electrodeposition technique to coat metal nanowires over this copper. And this is a template. This is the aluminum oxide template which we have used to grow this metal nanowire. Initially we used metal copper nanowire. This is the mechanism of growth, experimental conditions. These are with different diameter. You can see we have grown copper nanowire using different diameter value, and we have measured the pool boiling performance, and we have seen that as the diameter increases, the performance increases, both in terms of CHF as well as heat transfer coefficient. This is a basic bubble dynamic mechanism, what happens because of this nanowire coating. And then we have used with different distance between nanowires. You can see here that using the matching template, so you can see that the distance between the nanowires are increasing here. See, you can see the variation in their packing. And again, using this, we got, this is a contact angle measurement we did, a surface roughness measurement, and pool boiling analysis. Again, we got improved performances, but all the improved performances were again comparative with each other. But as compared to the plain copper, the performance was very high, both in terms of heat flux as well as heat transfer coefficient. We used both copper nanowires as well as silver nanowire. This is the bubble dynamics. And using the same nanowire coated and laser texturing, we have done some condensation experiment also in NIT Trichy. You can see the setup here. Now this is just a gist of what work we are doing currently using hydrogen energy storage. So this is something called liquid organic hydrogen carriers. It is very interesting one, and whoever is interested, I would like them to just have a search about this concept, liquid organic hydrogen carriers. Thank you. Thanks a lot. Hello.
Thank you for your wonderful session, sir.
Thank you.
So now let's go to the questioning session.
Yeah.
Or
Yes.
Okay, sir. Okay. The question is asked by Rajamani.
Okay.
Is there any role of pressure difference or turbulence is required to avoid accumulation of vapor in the vicinity of hot surface of metal, which leads to peak heat flux?
Yeah, as I already explained, that is CHF, and if we want to do it externally, it is called the active techniques. But active techniques are not used because, as again, they are energy consuming. That's why most of the enhancement techniques are concentrated on the passive techniques only. So yes, it has to be removed, and the turbulence has a greater role in deciding the heat transfer. Actually, that turbulence is responsible for creating the heat transfer in that region. So turbulence has to be there, but the accumulation of the bubbles over the surface has to be eliminated or to be avoided. Yeah, next question, please.
Thank you, sir. The next question from Dr. Kamali Jyoti Talukdar. Will there be boiling in absence of atmosphere, that is in space where there is no gravity?
Yeah, boiling is there. And what happens is how they, as I told Dr. Ishiraj from IIT Patna, so how they are doing, a lot of research is going in MIT also, US MIT, but how they are trying to implicate this condition is actually you just invert the surface, the boiling surface. So usually we do upward portion, but if you just invert the boiling surface, the bubbles cannot move. So actually that is the condition which is just to implicate the condition of space boiling, and there you have to study it using in that condition. Otherwise, how they are doing is using a parabolic flights. So if there is a flight and if it is falling at zero velocity, then it is like a space. So they are conducting experiments in those kind of falling flights, and they are imitating the conditions of space. Yeah, boiling is there in space. Because of buoyancy, the bubble
Thank,
motion is avoided, not the boiling. So you have to do something to improve the bubble motion.
thank you for your explanation, sir. The next question by Mr. Abhinash Nayak. As steel plants and ferroalloy plants are vulnerable to accidents and bursting occurs causing death of laborers, so how the accidents can be minimized in the plants? Can you explain, sir?
Yeah, hi. Truly speaking, I'm not into that heat exchanger part or the boiler parts, so I'm not the right person to answer in that aspect. I think we are only talking about the pool boiling at smaller scales, and at industrial scales, it's the phenomenon is totally different. Even in the nuclear power plants and this kind of plants where the bursting happens, it's because of pressure, supercritical pressures and all. So those, that area is totally different as compared to the one in which we are working. So I'm sorry.
Yes, sir. The next question by Nityanandam. If we are maintaining saturation temperature, how the heat is transferred from liquid to vapor? Can you, sir?
From liquid to vapor, I'm not understanding. See, saturation here, what we are, it is just to uh, okay, so you are talking about the initial condition, how the, so that is what the bubble growth. See, if it is at subcooled temperature, then the bubble will vanish. The heat transfer will takes place from the bubble to the liquid, and it will actually condense there itself. And that's why you have to transfer the heat from bubble to the surface actually. Otherwise, it will condense there itself, and you will not get that kind of efficient boiling. So that's why it has to be maintained at saturated condition.
Okay, sir. Uh, One more question, the final question by Vasant Kumar. In micro channel heat sink, whether we can use pool boiling instead of flow boiling.
No, actually, initially microchannels were employed for pool boiling only, and even now many works are going on. See, if you take the work of Khanlikar, they have done a lot of work involving microchannel, and now what the concept is, you have to give separate flow lines for the liquid and bubble. That means the bubble has to go in one way and the liquid has to come in another way. So it's like different flow paths for these two. So they are playing with different kinds of microchannel, different designs of microchannel to make it happen. And you can please check them, it will be very interesting. And even now many works are involved using pool boiling, and definitely in flow boiling many works are happening. And even my colleague Dr.R.Ajith Krishnan will be explaining in detail about this concept, because his expertise in that area only. I think he is the right person to explain more about that concept.
Thank you, sir.
Thank
Thank you
you.
for your wonderful session.
Thank you very much.
Uh, now, uh, now I wish to read the profile of Ajit Krishnan, sir.
Sure.
Let him take the session, sir.
Yeah, sure. Thank you.
Yeah, morning.
Good morning, sir.
Yeah, good morning.
Sir, now I I would like to read the profile of you, sir.
Yeah, sure.
Dr.R.Ajith Krishnan, Postdoctoral Research Fellow, Department of Mechanical Engineering, Kookmin University, Seoul, South Korea. Currently working as a research associate in two-phase flow laboratory in School of Mechanical Engineering, Kookmin University, Seoul, Korea. He was an overseas research fellow from India as a part of Korean Research Fellowship Program sponsored by National Research Foundation of South Korea. He completed his PhD from National Institute of Technology, Trichy in 2019 under the guidance of Dr. K.R. Balasubramanian. His doctoral research work was focused on the flow boiling in micro or mini-scale channels and their gravitational orientation effects. He has publications in reputed journals such as International Journal of Heat and Mass Transfer, Experimental Thermal and Fluid Science, Heat and Mass Transfer Springer, Experimental Heat Transfer Taylor, and Francis, etc. His research area mainly includes flow boiling in microscale channel, thermal management of electronics, dehydrogenation, microreactors, and hydrogen storage. I welcome you, sir.
Yeah, thank you. Can you hear me?
Now we can proceed to the session, sir.
Yeah, okay, sure.
Entire screen.
Yeah, fine.
Hello. Is it working?
Yeah. Is it possible to see the screen?
Yes, sir.
Can you see the title screen? Is it okay?
Yes, sir. Yes, sir. It is fine, sir.
Yeah, okay, I will start then. Okay, good morning to all, and I will thank Chennai Institute of Technology, especially Dinagaran sir, for giving me an opportunity to present from my side regarding the aspects of flow boiling. Already Udaya has explained a detailed version of the boiling phenomena, different boiling aspects, the basics of boiling, the pool boiling curve, etc. Okay. Now we will go much more in detail towards the another category of boiling, which we will call it as flow boiling. Okay, it's entirely different from pool boiling, where there is only a small surface or some space or cavity filled with water. Heat can be absorbed and boiled off. The bubbles are free to move. But what happens if the bubbles are constrained to move? That will happen in case of flow boiling. So in this, we will categorize much importance to the research aspects. Okay, we will go. The main overview of the presentation is regarding the boiling, some basic concepts, which I will just go fast, as Udaya has already explained. The basic applications, the main thing is that the research aspects for flow boiling and some references. Okay, this was already explained by Uday. It's what is boiling, or what's the difference between evaporation. Simply speaking, we can say boiling is a surface phenomena, and while evaporation it's simply a interface phenomena between a liquid and a surface, that is means liquid vapor interface phenomena. While boiling, we can see there is a surface included in that. As you can see here, there is an heating element or something which maintains some temperature or some heat flux, where the bubble can start to evolve from the surface by nucleation. Definitely there must be a surface needed for boiling. These are the two categories of boiling. As you have already gone through this pool boiling, where simply a pool of liquid is getting heated and nucleation will be developed. Okay. While in case of flow boiling, there is a prescribed channel or some flow passage for the working fluid to come inside and come outside. Meanwhile, the heat will be supplied from the sides or through the periphery, so that the liquid will absorb the heat and it will go through the nucleation stages, bubble development, growth, departure, and like that. Okay. So generally, flow boiling is called as forced convection boiling, or otherwise we can see that it's a combined pool boiling with some forced convection. That's the basic terminology of flow boiling, a bulk fluid flow along with some combined effect of pool boiling and convection. Okay, next, you can see here there is a basic difference between the pool boiling and flow boiling. You can see here there is a flow boiling happening inside the tube, and there is a pool boiling here. You can see the surface is free and the bubble is also free to move. You can see the bubble is getting evolved, enlarge its size, and get departed from the surface. But what will happen in flow boiling? You can see there is a small channel passage, and the bubble is very much constrained to move inside the channel. You can see bubble is getting developed, it get elongated, it get more elongated, it get evolved to the two sides, to the inlet side and to the upstream side, and it will move off. This is the difference in case of flow boiling. The bubble movement will be different, entirely different in case of pool boiling. Okay, and also the much important thing is that how, when the surface temperature has reached at a very high temperature, suppose for water at 1 atmospheric pressure, the boiling temperature we will say 100 degree. Okay, if the pressure goes on increases, we can say that temperature will also increase. So generally for 1 atmospheric pressure, the temperature needed for boiling to initiate the boiling is 100 degree, near 100 degree. Okay, if it is 100 degree itself, it will boil. Or if it is lower than 100, sometimes subcool boiling also can happen. This is the mechanism behind that. We have a small cavity or something inside the surface. We know that the surface will not be always flat. It has some cavities inside or some crack inside or something will be there. This will act as a nucleation site. Nucleation site means the first point where the small bubble vapor will be developed. Meanwhile, the bubble will develop inside that. Initially, the air will be there. This air will get expand and it will fill with vapor, and again it will evolve and it will increase its size and go on. Okay, you can see the small micro layer also get formed on the surface. You can see a small red micro layer. You can see here. This will be always there until the bubble will depart from the surface. Through this only the heat transfer will occur. This is that micro layer concept behind the boiling. Okay, next the two different categories of boiling. You can see subcooled boiling and saturated boiling. In case of subcooled boiling, the liquid is completely subcooled. You can see the surface will be at a higher temperature, but the surrounding liquid will be subcooled. Nearly for 1 atmospheric pressure, the required one is 100, but here it is only 80. Still, boiling will be there. The bubbles will be evolved from the surface and it will gradually get condensed in the surrounding liquid. And here also saturated boiling at 100 degrees Celsius, both water at 100 degree and the surface will be much more hotter than that, so that the entire cavity will be filled with bubbles and saturated water. These are the two categories of boiling: subcooled boiling and saturated boiling. This already we have explained the category of boiling, the different mechanism of boiling, where is the nucleation site for the vapor and also the bubble development and its growth. Bubble interface will be formed, a small micro layer will be formed, the bubble will increase its size according to the channel diameter, and also if it is pool boiling, it is free to expand its full size. Okay, so buoyancy force will be acting on the bubble and it will later lift off from the surface. You can see the bubble is lifting off from the surface. It has reached the bubble departure diameter. You will call it as bubble is going to depart from the surface, bubble departure size. Okay. The main force that is holding the bubble on the surface will be the surface tension force. You can see a small force that will attract the vapor bubble towards the surface by using this surface tension force. Okay, now moving much more to the boiling part, you can see flow boiling categories itself. There are two types of flow boiling categories. You can see external flow boiling and internal flow boiling. If the plate is heated with some fluid flow over the top, we can see it as external flow boiling, where the fluid is not confined inside the heated surface. It is free to move. This is what called as external flow boiling. Similarly, if the cylinder is getting heated, this can be also considered as external flow boiling. If the surface is more hot than the saturation temperature, it will boil from the surface. Similarly, for any surface, there is an external flow boiling. Sphere, flow over spheres, flow over cylinder, flow over flat plate, like that. Okay. And much more detailed area, that is the internal flow boiling, where the channel is confined or channel is not that much free for the liquid to move to any side. It is confined inside the channel. Liquid is confined inside the channel. Then we will call it as internal flow boiling. The liquid will start to move from the inlet and it will go out through the downstream and to the outlet. Okay. Meanwhile, during this passage, it will go through a series of flow patterns according to the boiling. It will initiate the bubble will develop, a vapor core will be formed and later dry out, or some other patterns will occur. So these are the two categories of flow boiling: external flow boiling, and we will call it as internal flow boiling in some tubes or some other internal side of the chamber or something. Next one is the basic thing. What are the different flow patterns that has occurred in a internal flow boiling? You can see here there is a single phase liquid, that is simply, for example, if we are using water is simply entering the tube from this point, initial starting point, while this wall of the channel is getting heated, wall of the tube is getting heated. You can see initially there is a bubbly flow. You can see the bubbly flow here. Small bubbles are formed on the surface like this. That is what called as nucleation, nucleated bubble. We will say it as onset of nucleate boiling when the surface is near to the saturation temperature. Later, this will absorb more heat from the surroundings, from the surrounding liquid or from the surrounding surface, and you can see the bubble will enlarge its size. That is what called as slug flow. We will call it as bubble slug. Okay. Next, again, this slug will get elongated and it will convert to a particular flow pattern, which is very much important in case of flow boiling. It is what called as an annular flow, where there is a thin liquid film on the walls, as you can see, two liquid films on the wall towards the circumference of that channel or tube, with some vapor core, this white space, this vapor core on the center. This is what called as annular flow. Later, if we increase the heat flux to another limit, you can see gradually this thin film on the side of the channel will get depleted or will get evaporated. It will get converted to vapor, and you can see a complete vapor or some patches of vapor inside the tube. This is what called as drop flow. Okay. Next, completely all the liquid traces will be drained, and it is what called as single phase vapor, or we will say it as dry out. Okay. So this is patterns of flow boiling inside the basic channel. We can see single phase flow, bubbly flow, slug flow, annular flow with some entrainment of liquid, drop flow, and finally the complete dry out. Okay. So this is the major flow patterns during flow boiling. You can see here how the temperature is going to vary. Temperature of the surface, how is going to vary. You can see initially the temperature will be near to the saturation temperature at the time of boiling. You can see here it's a saturation temperature initially. Gradually it is getting almost same. During the nucleation process also heat is getting absorbed. The temperature is almost remain constant. At one particular point the temperature is increasing suddenly. You can see here the temperature is suddenly peaking up. This point is what called as dry out point. You can see this point where the annular flow breaks, where the thin film breaks. It suddenly jump to a particular point or called as higher temperature point, or we will set it as dry out point. Until after that point you can see a gradual increase in the wall temperature or a sudden increase in the wall temperature. That must be avoided at any cost. That will lead to the damage of the system. Actually, I have heard a question from that previous session regarding controlling of this temperature, or how we need to control. Yeah, we need to avoid this point at any cost. Even it is a pool boiling case or even it is a floor boiling case, we need to avoid that situation at any cost by properly monitoring the channel and also by the temperature of the channel, surface temperature of the channel. It will not allow to increase beyond a limit, so we can avoid the dry out, so that the heat flux can be controlled to avoid the dry out. Okay. And this type of flow patterns are normally happening in conventional channel, where the channel diameter is greater than 3 mm. You can see here there is a channel classification. Here the channel diameter is greater than 3 mm. So this is the flow patterns that are happening inside the conventional channel. And you can see this is a vertical tube actually, and here you can see a horizontal tube. When we keep the tube horizontal, we can see that gravity will play coming to the picture. So the bubble will having lower density will go to the top, and liquid having higher density will come to the bottom. So we will get a stratified flow, some strata of vapor on the top with some strata of liquid at the bottom. You can see here some bubbly flow. Bubble is always trying to occupy on the top of the surface with the liquid on the bottom. This is the case of conventional channel with horizontal tube. You can see the cross section here. Liquid will be on the bottom portion only, while vapor will be occupying on the top. Okay. So all these matters occur for conventional channel with greater than 3 mm diameter. There is another category of channels. We will call it as mini channels, micro channels, or some other ranges where the size is less than 3 mm. If it is less than 3 to some 500 microns, we will say mini channels. If it is less than that, some 200 micron range, we will say it as micro channels. So the flow patterns or flow boiling patterns will be entirely different for these categories of channels. For this one is only for a conventional channel. some detailed view of the flow patterns. You can see bubbly flow, slug flow, churn flow, some annular flow, and similarly in horizontal tube you can see bubbly flow, plug flow. Always the liquid will be occupying on the bottom with a vapor on the top in case of conventional channel. So this is a basic boiling curve, which was already explained. You can see the onset of nucleate boiling, where the first initiation of that first nucleate bubble from surface. After that, the point A to B, that is what called as isolated bubble, and we will say the nucleate boiling regime A to B. And this point is what called as dry out point, or we will say critical heat flux, the maximum heat flux that can be absorbed by keeping a liquid on the channel. Okay, after this point we must be avoided the operation at any cost, because it will damage the system. So after that we can see some other boiling stages, what called as transition boiling, where there is some vapor patches. After that it will be completely vapor. So again the heat transfer will increase due to radiation heat transfer. So it's already explained in the previous case. This boiling curve we can trace by two methods. The first one is that of heat control method. We will controlling the heat flux to the channel. We can control the heat flux by using some heater, some variac or something, or resistance. You can control the heat flux. The second one is wall temperature control. We can regulate the wall temperature by using some phase change material. We can keep some constant wall temperature boundary condition on the surface, and we can trace. The exact boiling curve can be traced by using this constant wall temperature method, not in this heat flux control. It's difficult to trace the boiling curve completely by using this heat flux control method, but it's possible with the constant wall temperature by using some phase change material or some other thing. Yeah, let's check with some forces that was acting inside a micro channel or some any channel, whatever it is, conventional channel or some basic tube, because this is very much important in case of flow boiling. What are the forces acting inside a channel while boiling is initiated or it is propagating? Okay, so we have a channel and we can see some effective heat flux. That is, heat flux is supplied from the bottom of the channel, and there is a bubble which is initiated on the surface. It's developing. Okay, you can see here there is an inertia force. Since it is a flow boiling, definitely there is a flow, so there must be an inertial flow. Okay, some mass flow will be there. So this is the inertia flow. This will allow the fluid to come to contact with the surface, and it also will help in the bubble departure to pull the bubble from the surface so that the bubble can easily remove to the outside. Okay, and this bubble, since it is a vapor patch, you can see it is air filled space or vapor filled. It has some sort of buoyancy force. It has a lower density. Due to this density variation, some way buoyancy force will happen in the upward direction. We'll try to lift the bubble from the surface, like to pull the bubble from the surface to the top. Depends upon the channel size, this force will vary. Next is the surface tension force. You can see this surface tension force will be acting at this interface of the bubble to the surface. You can see the bubble will be touching the surface here and a small liquid micro layer. Through this portion, the surface tension force will try to hold the bubble on the surface. It will try to pull the bubble to the surface. In some cases, this force may be weakened depending upon the working fluid and the bubble, or depending upon the nature of the surface, it can change. Okay, the next one is the shear force. This is always try to keep some fluid film on the surface. It will be always against the flow direction. Next, one of the important force in case of flow boiling or internal flow boiling is that evaporation momentum force. You know that always the bubble will be developed on the surface. In case of flow boiling, it will be moving towards the downstream. Okay, this bubble will having some velocity. Since the density is varied, this bubble velocity is always higher than that of the liquid velocity. So it will create a momentum imbalance within the channel. Since the bubble velocity for this is very high, it having some higher momentum, it will move to that move at a higher speed, and liquid will move at a lower speed. So there is a net momentum difference. This will lead to some force within the channel, which will be always in opposite to the highest momentum. So we can see a negative force opposite to the flow direction. That is what called as evaporating momentum force. This will try to pull the bubble towards the inlet. It will pull the bubble towards the inlet. It will backward the bubble, that will not allow the bubble to escape from the surface. If this force is very high, you can get the dry out fast. It is like that. The concept is like that. Okay. So if we tilted it, the forces will also get tilted, especially these buoyancy forces. Inertia force will be vertically downwards, shear force will be upward, while the buoyancy force will be parallel to the channel. Similarly, in that way, but the net effect of these forces will not change. Okay. This is about the basic force analysis, which is very much important in the research part of this flow boiling. Okay. Next, the application part. You can see the flow boiling. A lot of applications are there. The main three aspects of this flow boiling are identified here. We can see the different mechanism of flow boiling. Okay, the first one is the mechanisms. What mechanism? Nuclear boiling. How the boiling is initiated. How the annular film is formed. This is the flow pattern related mechanisms. Next is CHF prediction for a particular channel, for a particular heat flux. What will be the CHF? That's how you can predict the CHF of a channel. Up to what extreme end we can go with that channel. This some sort of a prediction related or modeling related thing. CHF prediction. By experiment also we can able to trace that. But all the time we cannot impose experiments to verify our studies because it's very costly, you know. Next is the boiling heat transfer enhancement. How to increase the heat transfer. If we need to increase the heat transfer, you need more nucleation. You need the surface to be engineered like that. So what are the things that we can attain? Okay. All these three main irons are interlinked. You can see it will be linked with the cooling system design, one application, electronic packaging, another application, in related fossil fuel, nuclear or some other power plants, so another important application. So all these three are linked with the different applications as you can see here. The important applications has been listed here. You can see in refrigerator, in refrigerant boiling will be there, in steam power plant, chemical industries, nuclear coolant. I think one question has been arised from regarding this cooling in case of steel power plant or something, in steel forging or something. I think immersion cooling. It's related to the external boiling actually. Some hot material is immersed in a pool of liquid. It's some type of pool boiling you can consider. If there is a flow is there, you can consider external flow boiling. Okay. Electronic cooling, rocket cooling, supercomputer cooling, and some power devices, some avionic packages for defense. So before identifying these applications, we need to know the drawbacks of that. What are the main limitations for the case of flow boiling? And our research must be modified in order to overcome those limitations. The major limitation is that critical efflux, dry out. The channel will get dry out soon before reaching its extreme point or its extreme performance. And the flow instabilities. You can see a bubble inside a tube, the both way it can able to expand depending upon the flow velocity. So there is a chance for flow instabilities. Flow instability means there is a chance for the flow to come back towards the outlet, or there is a chance for the pressure to build in the one side of the channel, like that. That is what called as flow instabilities. Basically, you can tell like that. So in this presentation or in the upcoming slide, you can see these things, some research aspect regarding this flow boiling, mainly this conventional mini micro scale. What do you mean by a mini channel? What do you mean by a micro scale channel? Or what is the difference of flow boiling in these two type of channels? Okay, next one is critical efflux or boiling heat transfer in case of channels. How the wettability. Wettability means how the surface is, how affinity for the surface towards some liquid or towards vapor. Such things will affect the boiling. The nanostructures or some patterns that will affect the boiling. Next is instabilities, bubble dynamics, how the bubbles get moved inside the channel. Next, modeling and correlation. All the time experiment will be difficult for us. So how to model the flow boiling inside a channel. Next, the different fluid part, that is nanofluid, surfactant, self-rewetting fluid. And another question I think I have heard during the session, the gravity, how the gravity will affect the boiling inside the channels. Those things we will just have a basic look and we will explain much more in the research point of view. Okay. Before starting with the huge research of this flow boiling in channels, you can see the biggest controversies that are existing is the channel categorization itself. That's a big joke actually. Before starting the research regarding flow boiling, we need to mention this part in a better way. What is a channel actually? How the channel is getting categorized? It's very difficult to explain the channel size with a single term. A lot of parameters has to be taken into account. Okay, so till now there is a no generalized condition or a criterion has been established regarding the channel size. Many researchers has proposed different categorization. This is such a categorization. You can see greater than 3 mm conventional channel. Okay, less than 3 mm up to 200 micrometer mini channel, 200 to 10 micrometer micro channels, and like that it will go on. But you can see in some other publication or in some other research, he's taken even 1 millimeter as micro channel. Yeah, you can see if you want to search it, you can just go through flow boiling in micro channel and see the channel size. It will be nearly around 900 micrometer or some 800 micrometer. Still, he is saying that it's a micro channel. Yeah, it's possible. So, the biggest controversies that are existing inside this research was the channel categorization itself. In my point of view and in my perspective, if the gravity force is completely dominated, then we cannot consider that channel as micro channel. If the gravity force is completely suppressed and surface force has been evolved as the dominant force, we can call it as a micro channel. So in micro channel, the gravity force will be negligible, and in conventional channel, the gravity force will be very high. So this is the main parameter that we have adopted for categorization our channel. Okay, so basically this is the biggest part of the research that anyone can carry out still, because this generalized criterion is not available till now regarding the channel size. So basically we will categorize the channel based on this hydraulic diameter. I think most persons regarding this fluid and heat know about this hydraulic diameter, this 4A by P, 4 into wetted area divided by wet area, cross-sectional area divided by wetted perimeter. Okay, this is the general term used to categorize the channel. So reducing channel size, is it much important or not? Yeah, actually reducing the channel size, many persons having the doubt why reducing the channel size will improve the performance or will improve the heat transfer coefficient. Okay, so before starting your research in this area, it is very much important to identify this term, that is what called as surface area density, that is surface area to volume ratio. Here you can see a conventional channel, a bigger channel with a fluid flow. You can see there are 3 channels, and you can see a micro channel with a lot number of channels. You can see what's the difference between these two, in what aspect they are different. The figure in the right side will give you a much clear idea. Here there is cube with 1 centimeter, we have been divided to 4, divided to 8. Okay, you can see the surface area of each cube will be increased by 12 centimeter, and initially it was 6 centimeter. Okay, again we reduced to some other 64 parts instead of 8. That is 8 into 8, we double the multiplication, and we can see the number of parts will be 24. The area will be increased as 24 centimeter instead of 6 centimeter. If we again increased it to some other 100 nanometer, see what's the increment in the area. It is nearly around 60 meter square instead of 6 centimeter square. See what's the increase in the area. This increment in the area corresponding to the volume has a huge role in the heat transfer in order to increase the heat transfer coefficient. More area, more heat transfer coefficient we can expect. So this is the mechanism, that is surface area density or compactness, we can say. Surface area to volume ratio is the basic behind governing that particular channel is good for some higher heat transfer application or not. Okay, so this is the basic part behind that. What's the difference between a conventional channel and a miniature or micro size channel? Why it's important also? So we have different applications. Mainly we will be concentrating on the thermal management techniques of this micro channel and flow boiling applications, because flow boiling has been eminently used for thermal management of electronic devices. You can see mini and micro channel transport by embedded with some heat sink, we can able to cool the device more easily. So this will fall under the category of forced liquid and air cooling. So by using this type of flow boiling inside a channel, we can able to cool the electronic devices properly and uniformly. Okay, this is one of the example for that. You can see there is a small channel wall, some heat sink like channel which was built onto the surface of a processor. You can see by using some heatsink paste or something, we can build the channel on the top of the processor. We can fix it, and fluid is coming inside, fluid is coming outside. Here you can see during the passage, you can see it is getting absorbed with the heat and get converted into a series of flow patterns, and later it is coming out. The entire heat, both sensible heat and latent heat, was getting absorbed by the channel. Okay, and these are the series of flow patterns that was evolved during the transport. Initially the bubbly flow, you can see here elongated bubble. After that you can see an annular flow pattern here, and finally the dry out, which must be avoided at any cost. These are the real-time view of a channel which was undergoing a series of flow patterns. You can see here the annular flow patterns, but here the dry out was not completely visible. It's not started yet. So this is the basic application, or one of the major research aspect behind this flow boiling in miniature size channel, which we are concentrating much more. So regarding the channel size, you can see this is a comparison for different size of channels. Okay, this is the sample we have taken to mount our channels. You can see different channels has been machined by using EDM machine. And for size comparison, we have given a 1 rupee coin also here. You can see here the channels, different size channels. This is actually 0.3 mm diameter channel. You can see this is U-shaped is because of that wire diameter, EDM wire diameter actually. This one is 0.3 mm spacing with 0.6 mm depth. This is 0.9 mm depth with 0.2 mm fin width and 0.3 mm spacing. This is some another type of shape. We will call it as reentrant channel, and we will say some different shape channel you can see here. So this is a channel that was machined by using EDM, electric discharge machining. Okay, this just shown as a application part how it looks like. Okay, this is the machined channel. This is the heat sink. You can see by using a copper, you can see how the channel is machined. Because we are mainly concentrating our talk much more on this small size channels, not on big size channel, because it's already explored much. The big size channel has already explored much. So better to have a look on perspective on what happening inside small channels during this flow boiling. Okay, these are the channels with 0.312 mm. See 0.3 mm diameter, that is 300 microns, nearly 300 microns diameter. This is the heat sink with some 31 parallel channel you can see here. This is the testing block actually. We can heat the block and we can allow the fluid to pass through and we can test the performance. Okay. So this is the facility that we have used for testing the heat sink flow boiling facility. You can see there is a test cell you can see here. This is the major part test cell. This is the test cell. You can see some enlarged view. You can see the sample here. On the top, we will machine the channel by using EDM or some other CNC machining. You can see 3 holes here to point the temperature measurements. You can see here for temperature measurement by using Fourier law. You can approximate. If you know the heat flux, you can get the temperature at this point and the surface. Okay. And similarly, we have a heater arrangement. You can see the heater here. Heater cartridge heaters. You can see here. The heat will be supplied to this heat sink, microchannel heat sink, and we have a casing like this to cover it so that we can allow the fluid in and out. You can see the fluid in and out, and also this is the cross-sectional view. Fluid is coming here, it is going inside, it will be flowing through the channel, it will cool the channel, and it will be coming out like this. So heat will be coming from these cartridge heaters to the channel, and similarly it is getting cooled on this way. Okay, this is the basic layout of that test cell you can see here. And for allowing the fluid to come inside, cooling that fluid, again supplying it back, we have a lot of devices here. You can see the pump here, micro pump. It can supply some small amount of fluid precisely, some flow meter, some data logger in order to measure the temperature. This is the real view of that setup. Some pressure mountings in order to monitor the pressure. Some power supply. Initially, we will not do with the electronic circuit. We need to provide the heat by some external means. We'll use some power supply and some chiller. The fluid that coming out from the surface will be hot, so we need to cool it back. So we are using one refrigerated bath or something to cool the device. or cool the liquid that is coming back. It's a basic layout or how to experiment with a channel. It's a simple logic that we can apply. This already we have gone through regarding the test section. This is a detailed view. So you can see the test cell here. This small portion you can see here, copper test cell with some channels. You can see here. This is inlet and this is outlet. You can see the temperature mountings here, and for inlet and outlet temperatures, thermocouples to measure the temperature of the surface, the pressure sensors here, and all things will be connected with a data logger in order to monitor the system. So some real view of that setup, complete setup. Okay. So don't overthink about that. Don't think about always we must be getting with sophisticated devices and supply for doing our research. So I'm just providing those who are interested or those who are started to research in that area. They can little bit start their research with those things. It's an alternative. We can use this also. Maybe some little bit uncertainty will be high, but you can point that uncertainty in your findings. That's all. Instead of micro pump, you can use some windshield washer pump for vehicles. You can see wiper pump, we will say, or you can use some aquarium pump also by using some good valve with some good CV value. You can control the flow rate by using this aquarium pump also. Instead of chiller, you can use simple copper condenser coil in order to cool your fluid back by using some tray or some ice cube with inside. Dip the coil inside and you can able to cool it. Instead of DAC, you can use simply some eight point indicator with some thermocouples. You can see it just costs around 3,000 rupees. This coil will be cost around some 2,000 rupees, and this pump will be cost around 3,000 rupees or 2,000. That's all. Don't think about big equipments because at the beginning stage of your research, it will be practically impossible sometimes. Okay. And instead of flow meter, you can use simple rotameter, which will be cost around some 2,000. Or simply, if that is also not available, you can simply use a measuring jar with a stopwatch enough to get your flow rate. So these are the alternatives that you can think about at the beginning stage of your flow research. Not flow boiling research. In any flow research, you can think about these things instead of you are not starting your research until or waiting for your equipment or something. So based on our study, this is the basic curve. I'm not going to detail of these things because it's a simple curve. I just want to introduce you how the boiling curve, when practically we are doing some experiment, how we can going to see the boiling curve for different mass flux. Mass flux means mass flow rate divided by cross-sectional area, or simply you can say flow rate for different flow rate for a particular channel size, 300 micrometer, how it will looks like. You can see these are all the part of single phase flow until one.
Sorry for the interruptions. Sir,
Yes.
we are unable to see your PPT, sir. PPT, you are sharing it?
Yeah, sharing.
Yeah, it's we are unable to see. Can you
Yeah,
share it
okay.
again?
So okay, sir.
Not yet, sir. Not yet, sir. Not yet. Sir, please, you have to turn on the screen share, sir. It was not done, I think so.
Is it okay, sir?
Yes, sir. Please go ahead, sir. Please go ahead, sir.
Yeah, okay, fine. Thank you. So let me know if any issues are there.
Please, you can go ahead. I let you know.
Okay, fine. Thank you. Yeah, this is the boiling curve. You can see up to this point, you can see there is a single phase flow only. There is no boiling initiated. Okay, when the surface temperature has been reached 100 degree, this is actually not the surface temperature. Surface temperature minus inlet temperature. Here the inlet temperature is around 35 degree. So when it Ts minus Tin reach 65 degree, it will be nearly around 100 degree. You can see this point, the nucleation is begins, and after that the curve will go like this. Okay, you can see we will not trace the entire boiling curve. We will go only up to that peak point. That is what called as dry out point or critical efflux point. Okay, so this is the critical efflux point for corresponding to that flow rate. If we increase the flow rate, you can see the critical efflux will also high, but also the onset of nucleate boiling, the point where first nucleus start will also get increased. Here it is 100.1. Here it is maybe 101. Here it may be 102, like that. If we increase the mass flux, you also get a higher onset of nucleate boiling. This is the basic curve, which there is not much detail in that. I'm simply just shown how to trace the curve. That's all. So these are the different mechanisms of boiling you can see here inside the channel. The first point is the nucleation of the channel. You can see the small nucleus that's formed on the channel. You can see small nucleus here. We will say it as onset of nucleate boiling. Small tiny nucleus are formed on the surface. Okay, this is the starting of the boiling, and this is the ending of the boiling. You can see here a complete dry out. No water will be there. Completely vapor patches. This white color will be completely vapor, and it was inside the channel. So these are the two mechanisms or starting and ending of a flow boiling curve trace. At the starting point, you will get an onset of nucleate boiling like this, and at the ending it will be complete dry out like this. Okay, these are just for your visual knowledge only. So in between, what will going to happen? You can see here there is a nucleation, a large amount of nucleation with bubbles are formed inside the channel. This is one bigger channel, 1 mm diameter. You can see the bubble is enlarged. You can see here, and you can see there is some flow pattern, annular flow patterns, some wetting and rewetting of the channel, and finally the dry out. This is that happening inside a 1 mm diameter channel. These are the different flow patterns. It's a detailed explanation of that flow patterns or images. You can see bubble flow. You can see some elongated slug flow. You can see some another elongated slug here. And finally, you can see the annular flow with some thin film on the two sides of the wall and some sort of wavy annular flow. This annular flow is unstable, so we will say wavy annular flow. Such type of flow patterns inside the channel of 300 micrometer diameter. Yeah, some enlarged images, some transitions. You can see some vapor bubbles started to form. You can see some elongated bubbles. No need to zoom it because already it's visible since it is a higher diameter channel. These are the formation of some elongated bubble. See, you can see the annular flow. You can see the thin film liquid that is on the side of the wall. You can see this is what called as annular flow. This is a complete annular flow inside the channel. You can clearly visible. So these are the flow patterns that we can able to see while our flow boiling study inside any channel. But here we have adopted 1 mm channels, that is mini channel. So what's that critical influx and flow instabilities? Actually, we have already seen that if the heat is increased beyond the limit at one particular point, we cannot able to maintain the surface temperature at a limit. It will increase drastically. That point is what called as dry out. After that, the temperature will increase much. So we can see that temperature has been increased and CHF has been attained. At the time of that, you can see there is flow oscillations. The flow will be fluctuating from the inlet to outlet. You can see rigorous flow oscillations like this. This is the inlet side and this is the outlet side. You can see the flow will be fluctuating back suddenly to the inlet side. This bubble will be suddenly expanded and getting elongated to the inlet stream. So this must be avoided at any cost. So the main area behind the flow boiling is to avoid this CHF, to maintain the boiling for a long time, to avoid CHF and to increase that heat transfer coefficient. So these are the different studies, that possible studies in this case: wettability studies, heat transfer enhancement, flow patterns, flow instabilities, like that. Okay, so we will first target on the various research possibilities in case of heat transfer enhancement. You can see basically there are two methods to enhance heat transfer in case of microchannel flow boiling. One is active method and other one is passive method. This active method is by incorporating some mechanical pump, mixing, or some rotation or vibration, or some adding some external magnetic field. By inputting some external power, we can alter the boundary layer and we can improve the boiling by properly allowing the bubble to depart from the surface like that. Okay. In another method, there are some passive methods. By creating some engineered surfaces, the boiling can be controlled. By tuning the surface roughness, by creating the eddies, by creating turbulence, we can able to maintain the higher heat transfer coefficient. These are the two methods, passive and active. Okay. The next method is the heat transfer coefficient enhancement by using micro pin fins. You can see these are by using laser machining and all, we can able to create a lot of microstructures on the surface like this. You can see some microstructures. These structures will provide a lot of nucleation site. A large number of nucleation can be promoted from the surface. You can see some fins, small fins surfaces on the channel. This is the channel surface. You can see small microstructures. these tiny cavities can produce a lot of nucleation site, and also they can able to wick a lot of water towards the surface, and that can enhance the boiling and increase the critical reflux values. Okay, the main thing is that more stable nucleation site and also that wicking effect that will increase that CHF. These are the curve that is showing the proof without microstructures and with microstructures. With microstructures, they can able to attain more CHF value. This is one of the interesting research area we can move ahead, because a lot of manufacturing facilities can also be incorporated in these persons. So a lot of collaborations with the other departments, mainly production and manufacturing, or some micro machining area can be incorporated, and you can study with this area. That is flow boiling enhancement by using some microstructures or pin structures. Similarly, other type of structures, you can see piranha fins, stepped fins. You can see different shapes: trapezoidal profile, elliptical profile, triangular profile, or some small nucleation site built on the some small holes that has been built on the channels like this can also promote the nucleation. And by using wavy type channel, these are the some other type of channel we can able to manufacture, and we can employ the study on that in order to improve the boiling heat transfer. Okay, so why such a microstructure, and what's the future research scope? Actually, the microstructure main aim is to increase the bubble nucleation, the wetting with the coolant, and also bubble mixing or bubble venting, proper removal of the bubble. Okay, you can see here this is micro pillars which can able to promote the nucleation by intermixing of liquid and generation of the bubble from these all cavities like that. So the main research scope behind this area is the optimization of fin shape. How we can optimize the shape of a fin so that more number of nucleations can be developed and more heat transfer can be attained. Next is the geometric parameter selection. What geometry of the fin we need to select. In that area you can pinpoint, and you can collaborate with some other techniques, some manufacturing techniques, in order to create some structures on the surface. That is advanced machining techniques such as laser or some other CNC machining or some other micro machining or lithography or something you can employ, and you can test your machined surface with some facility, and you can improve improve the CHF or heat transfer is improved or not, like that. Next is the development of economic and long-lasting structures. This is another part, because this must be reliable, because it will not lose their efficiency after a long period of time, or it will not cause the surface to wear along with that long time usage. So economic and long-lasting structures is the must for in case of application, in case of electronic cooling on some other things. So in these areas you can concentrate much, and you can make step on your research regarding these microstructures for heat transfer enhancement. Next is flow instability. Actually, these flow instabilities occur inside the channel due to the random oscillations during the bubble development. During the flow reversal, the bubble will be pulled back towards the upstream end or to the inlet side. So basically, there are parallel channel instability and upstream compressible instability, because the bubble get compressed inside the channel and it will lead to severe pressure oscillations. So what are the things we can expect from this part? You can see the bubble will be elongated in the both, and sometimes it will go back to the inlet side and it will create some instabilities like this. Initially the pressure will be high. After nucleation the pressure will be high. Suddenly the flow reversal will cause the pressure to drop entirely. This will lead to severe pressure oscillations inside the channels due to flow reversal. So how we will avoid this? This is the main part of the research in case of flow boiling. We need to avoid this at any cost. So different methods are available. You can see different methods that has been employed for mitigating these instabilities. These are all channel inlet restrictors. Within the channel, we will provide some restrictions like this. You can see small restrictions, a small narrow passage, a restricted passage we will provide. It will be giving the inlet to the bigger channel. So this type of inlet restrictors can be avoid the vapor flow back along with instabilities. So this is the one of the proposed idea. And next is the reentrant cavities. These are built on the side of the channel. See, you can see that this is the channel wall, On the side of the channel wall, a lot of cavities are built like this. This is the top view of that. This is the channel wall. A lot of cavities are built on the sides like this. So what will happen now? When vapor is developed, this vapor will be tried to adapt towards this reentrant cavity, and it will occupy there, and that will cause the reduction of instabilities within the channel. This will vent the vapor properly. So this type of arrangement has been proposed by many researchers in order to reduce the instabilities. Next is the offset of strip fin. The strip fin also can able to reduce the instability, but the pressure drop will be very high. So this strip fin will cut off the bubbles that is evolved from the surface. Any bubble which get evolved at this point, it cannot move directly to this point because this fin will cut the bubble to two. One bubble will be cut off to two. So it will move. Similarly, the bubble will be get splitted to different parts of the channel and the flow instability can be reduced. But the main issue behind all these things is the higher pressure drop, which must be avoided because the pumping power will be very high if we adopt these methods. So is there any alternative? That's the next question. Yeah, definitely there must be an alternative. You can see the another two categories, that is what called as micro gap and open micro channel. In open micro channel, you can see this is the channel here, and we will provide a small space on the channel. Before assembling the channel by using some cover, we will provide a small space over the channel. So that will allow the bubble to occupy in that space. You can see like this. The bubble can occupy that space and that will improve the instabilities. So this is what called as open micro channel. And the other one is, the next one is micro gap channel. Instead of channel, we can simply use some plain gap in order to allow the bubble to boil off. So the bubble can able to expand at any direction, but the transfer coefficient will be less because less surface area will be involved in this. So the instability reduction will be very, very high in this case. We also explored some sort of open micro channel and micro gap. These are the result obtained from that, some flow images. You can see during the micro gap, simply the bubble will be evolved and can able to expand in all directions. So instability can be removed. But we observed a drastic reduction in the heat transfer coefficient in this case. So in open micro channel, we also studied that also. You can see here, bubble will be properly evolved to the top surface of the channel like this. Okay. See, this is the schematic representation. Bubble will be formed and it will be get moved to the top surface like this. Actually, this open microchannel concept was introduced first by Kandlikar actually in his paper, and he has a patent also for that. Next is another innovative methods that has arrived in the later years. You can see these are expanding channel that is proposed by Kandlikar. Next one is open channel with expanding. Some hybrid configuration. This is proposed by from Singapore University actually by Lee, Professor Lee actually. You can see the micro channel section at the off portion and micro gap section at the off portion. So the pressure drop can be regulated, stability can be improved in that part. So like that, a lot of innovative researchers are coming in order to avoid the instabilities that are happening inside the channel. These are all some methods to remove the instabilities. So you can think of some other method by employing some devices or by building something inside the channel, how you can able to reduce the instability inside a channel. Okay. So these are the another important part that you can able to highlight in your research, how to reduce the instability by using some structures. So the next one is the wettability effect inside the channel. You can see here wettability has a huge role in boiling, as previously explained. It can able to involve proper wetting of the surface. So how the wettability can be improved? That's another part. If the fluid is more wettable to the surface, it will be more hydrophilic, we will say, and it can improve the CHF like that. Okay. So how to tune the surface with proper wettability? Wettability will create more wicking effect, and also it will provide a good micro layer on the surface that can promote boiling. You can see here how the wettability can be improved. We can adopt porous coating to improve the wettability like this, or we can use some nanowires, metal nanowires, or we can use some carbon CNT coatings in order to improve the wettabilities, or simply some micro nano structures also can able to improve the wettabilities. A lot of studies are coming in that way also. Here, simply we can control the wettability by changing the surface roughness also. Different roughnesses will provide different surface wettability. So these are the different methods to control the roughness, control the wettability of the surface. We can employ any one of this method, porous coating, nanowires, or something. By using some methods, we can able to tune the wettability, and we can do some experiments, and we can report that this much improvement happened for this type of coating. Some innovative coating we can able to find, and we can explore in that way. This is the another aspect for this flow boiling research. So you can do the aging study, durability test, the addition of coating in that area you can explore, or you can use some mixed wettability, hydrophilic and hydrophobic patterns. You can try what will happen to the bubble dynamics during this coatings, what will happen to the micro layer evaporation, what will be the temperature profile. So different types you can employ. Actually, bio-inspired functional materials, that's the new evolution of research in case of boiling. A lot of biomimicking was introduced to the boiling, different structures. For example, the lotus leaf, you all know. Like that, a lot of things from the nature itself was introduced to the research so that it can able to highlight the boiling process and improve the boiling process. So you can think in that way also. Next is the working fluid part. How we can alter with different working fluid, or what we can do in that area. Actually, the different working fluids will be used for this boiling experiment. The main thing was water, since it has some high surface tension and high latent heat of vaporization. The bubble departure diameter also will be high. But when we take some refrigerant or some other electronic fluid, you can see the surface tension will be very less, and also there is a lower bubble departure. So what's the difference between these two, or which can able to promote better? In that way we can able to deviate our research. Or the different scope include some binary mixture. You can mix with some liquids to get the good properties. You can use some water with some other ethanol or some other fluid, so the best properties of the both liquids will come into picture. So in that way you can promote your research, or you can track your research. You can see the self-riveting fluids in another area with variation in the surface tension according to the temperature. We can see the surface temperature will not reduce with the increase in the temperature in case of this riveting fluid. And also surfactant, in order to reduce that surface tension, surfactant will be added to the fluid before doing the experiment. So in that way you can modify your research in that way with different fluid. These are the different research scope with different fluids. Next is the effect of nanofluid. Actually, this nanofluid effect on boiling was explored a lot, but a lot of discrepancies are there in the result also. Some persons will report a huge increment, while they are also reporting after some time the increment was not there like that. Actually, this nanofluid will cause the particles to deposit on the surface like this, and will cause the surface cavities to fill with nanoparticles, or open up some cavities, or double up some cavities. Like that, it can not able to guide boiling in a proper way. It will show some irregular result. One time it will be high, and another time it will be less. So you can also try with this different nanofluids. Some good nanoparticles can able to promote boiling, but as far as concerned, the result from these nanoparticle flow boiling and nanoparticle boiling studies was a little bit different. Many results are not matching with that other result, because many persons are involved in CHF enhancement. They are telling it's enhanced, but some other portions are telling it was not enhanced. Actually, it is reduced the CHF like that. So we must be very careful while dealing with these nanofluids, because you has to get the result each and every time as an increased CHF, not with the reduced CHF. So you can decide in that area also. Different nanoparticles also can be used. Next is how the gravitational orientation can influence, or how the change in the orientation can influence flow boiling. So definitely it can influence flow boiling, and mainly there are different test facilities also in order to do that. Actually, the main problem with these facilities are they are having only some 20 seconds or 10 seconds time period, which is very difficult to done an experiment. So what we can prefer is to do some real-time experiments on Earth gravity with different orientations. We can tilt it with different orientations with inverse to the gravity, and we can do some experiments. Okay. So there are also a part of research regarding this floor boiling. The another one is that modeling, that is all the time the experiment and doing a lot of things will be very difficult. So computational fluid dynamics can able to reduce a lot much. Actually, modeling boiling is little bit difficult because of that flow patterns, different flow patterns has been evolved during the boiling process. So generally we will use separated flow model. That means we will model each pattern independently. For one model for bubble flow, one model for slug flow, one model for annular flow, like that. Okay. Or some researchers will think about all the flow is bubbly flow and they will model a homogeneous model for bubbly flow only. Like that also you can think about. Okay. So CFD modeling is one of the new era tool in order to analyze the boiling, especially in flow boiling case also. Okay, this is one of the interesting result from a CFD analysis in flow boiling. You can see he has developed interface tracking of a single bubble like this. Only bubble flow is dealt with, no other flow pattern. Simply how is a bubble is developed from the surface according to the by guiding with different forces and how the temperature is varying like that. So you can do like that also in case of boiling, but definitely you has to work with some user defined function in order to define the bubble, in order to define the bubble growth, bubble motion, how it will get moved, because fluent itself has no inbuilt tool in governing this bubble motion. I think that you has to be designed by using some user defined functions, definitely. So let's conclude. We can see that the flow boiling is an interesting field of research, much more on these small channels, especially micro and mini channels. And mathematical modeling and experimental tools can be used. And the wettability has a huge influence, which can be controlled by any manner. So it will influence boiling. The surface tuning is also important. And much highlight is on the bio-inspired nano and microstructures that can able to promote boiling, which was a lot of obligations was coming nowadays. So these are the one of the major research findings from our group. You can see one paper in micro heat sink, some channels, some orientation studies by using some nanofluid also. And these are the good books that I can prefer to you people if at least one can able to start with this boiling, in flow boiling or some boiling area. You can use the major books, John G. Collier, Convective Boiling and Condensation, some Heat Transfer Handbook by Adrian Bejan, some two-phase flow boiling and condensation book from Kandlikar. It's one of the important book we can refer because a lot of publications was also added in that. Some old findings from the history of flow boiling in mini, micro channels and conventional channels has been included. So if time permits, you can able to go through these books and get some basic knowledge regarding this boiling if you are much interested and beginning in that area. Okay, and these are some references. Okay, and stay safe. Thank you.
Thank you, sir.
Yeah.
Now let's move on to the questioning session,
Yeah,
sir.
sure.
Okay, sir. The question asked by Rajamani:
Yeah.
how the surface tension is in opposite to flow as you show in the slide of force balance, because
Yeah.
surface tension will act along the free surface of
Yeah.
liquid.
No, actually, it's actually the definition of the surface tension. Actually, the arrow mark is not against. The surface tension is actually trying to pull the bubble towards the bottom. If we have a bubble like this, it will be pulling the bubble towards the bottom like this. It's our basic concept is that the definition of surface tension we have read from our textbook in a way that it will always behave the surface as a stretched membrane. Actually, surface tension itself can be defined with different interfaces, liquid to vapor, liquid to surface, like that. So actually the surface tension force I have shown towards the direction of the liquid, it has to be not shown like that. It has to be shown in an inclined portion to the downward direction. Okay, not to the left side. I think I have shown at the time of explanation that it will act at the interface only. It will act definitely at the interface, and it will be always trying in the direction to pull the bubble towards the surface. I think I'm clear.
Thank you, sir.
Yeah.
The next question: what type of flow boiling is useful in heating pipes and how to make it? Can you, sir?
What type of flow boiling use? Yeah, in heating pipes, definitely it will be internal flow boiling. I can't get the question clear. Can you please repeat once more?
Okay, sir. What type of flow boiling is useful in heat pipes and how to make it?
Heat pipes.
Yes, sir.
Yeah, in heat pipes, actually, different types of heat pipes are there. If it is a closed loop heat pipes or pulsating heat pipe, there is some sort of boiling that is happening inside. But it's actually by using a wick heat pipe, wickless heat pipe. Different categories are there. Actually, it's I don't know what he's thinking about. Actually, if it is a wick heat pipe, the wick will absorb that water from the surface and it will undergo phase change, and it will, through wick part only, it will go to the condenser section, and from there it will be converted to liquid and driven back to the evaporator section. It's not completely a flow boiling, we can say. In pulsating loop pipe, we can see this type of pulses of vapors, but it's an internal flow boiling actually, not an external flow boiling, definitely. Maybe I need
Okay,
much
sir.
more clarity from his side regarding the question, I think. Yeah, okay.
Okay, sir. The next question by Dr. Kamalijoti Talukdar.
Yep.
How cavitation is different from bubble formation?
Yeah, cavitation is entirely different from this bubble formation. See, cavitation will happens when the vapor pressure of that corresponding temperature has been reduced beyond the limit. We have seen in fluid dynamics and all, while in draft tube, especially when the vapor pressure has been reduced, when from the turbine the liquid is going to the outs, when the pressure has been reduced beyond the vapor pressure, the liquid will start evolve bubbles, and in that way it's due to the pressure difference. But in case of flow boiling, such type of cavitation things will not happen. Usually the pressure will guide the boiling temperature. If the pressure decreases, definitely the boiling temperature will also decrease. But it's entirely different from this category. It's formed within that surface according to the temperature, but here definitely there is a surface was there in order to provide the temperature. So it's from the surface only the bubble is getting evolved. It's entirely different from that cavitation phenomenon.
Okay, sir. Thank you. The next question. Whose speed of boiling is more, pool boiling or flow boiling? Will the speed of boiling be different in earth and space where there is no gravity?
Okay. Actually, first we will take apart the gravity. Suppose I am doing two type of experiment in Earth itself. First we will take that case. I am doing one pool boiling experiment, and I am doing one flow boiling experiment. See, the main difference between the pool boiling and flow boiling is that the liquid in case of pool boiling is simply filled over the surface. The bubble is free to move at any place. While in case of flow boiling, the mass flux has a huge role. In case of pool boiling, the liquid is stagnant. While in case of flow boiling, there is a mass flux. Mass flux means it's simply, you can say, the flow rate, some flow rate. If we increase the flow rate, to a higher value, the bubble departure from the surface will be also fast, because the inertia force will dominate there. While in case of pool boiling, there is no inertia force. So how we can able to compare? One, there is a inertia force is there. There is one natural convection force only be there. So we cannot able to compare pool boiling speed in that way. Pool boiling speed such a way, or flow boiling speed, because flow is there. Then definitely the flow, some value we need to be imposed to the flow, some velocity, some mass flux. So it will depends. That's a category regarding Earth's gravity. If we go to the space, you can see there the gravity force will be zero. So what will happen? Actually, what caused the bubble to depart from the surface? It's the gravity force or the buoyancy force of the bubble caused the bubble to depart from the surface. Bubble will be attached to the surface by its surface tension force. So if we attain some particular shape and size, buoyancy force will increase, and finally it will depart from the surface. In space there is zero gravity, no buoyancy force. So what the bubble will do? It will try to attain to the surface, always attached to the surface. In that case, you can say flow boiling is much more important, because there is a little bit of flow. We can alter the flow. We can allow the bubble to depart from the surface by using the inertia force, even though the gravity force or buoyancy force were absent. So in that case, the boiling is little bit we can improve in case of earth, outside Earth gravity. We can say there we can only promote flow boiling. So a lot of things you can, some fluid it will allow it to self revert the surface, and it will change the surface tension nature, and that also we can possible to improve the pool boiling also. Actually, pool boiling is a little bit difficult in outside Earth gravity, but it's possible. We can able to change the working fluid or the surface so that liquid will be properly revetting the surface. We can able to do, but in case of speed, we cannot able to compare in that way, because one side there is flow is there, and the other side there is a bulk liquid only. So definitely the flow will also promote the speed of boiling. Definitely we can control the speed of boiling by using the flow. If we depart the bubble from the surface, we can apply more flow rate and able to depart the bubble. And surface temperature also matters. More temperature means more bubbles. So I'm considering surface temperature constant for all these cases, for all these explanations. For same surface temperature, for all these cases, if you look, if we alter the flow rate, definitely the flow boiling will also be increased, or we can attain more heat transfer coefficient. Definitely. Okay. Alon, we
Thank you,
cannot
sir.
compare. Yeah. Thank you.
Yes, sir. Thank you.
Yeah.
Thank you so much. Thank you so much for the valuable time.
Yeah, sure.
And I thank both Dr.G.Udaya Kumar and Dr. Ajith Krishnan for their valuable time and their wonderful presentation.
Yeah.
And pool boiling and flow boiling. So there are a lot of scopes in research, and they have shared their excellent results and excellent knowledge sharing. And I think certainly this will be highly useful for the researchers, those who are going to enter into the field, and certainly there might be a knowledge enhancement for the researchers, those who are already working in the particular field. So thank you so much, sir. And certainly this will open up the students' minds also to get into some heat transfer research. So thank you so much. Thank you so much for your wonderful presentation. I thank Dr. Ajith Krishnan, Dr. G. Udaya Kumar for their contribution. And even though I have requested them to give the presentation of the short notice. So thank you so much, sir. We would like to hear you a lot in some other time also. We would like to meet in some other occasion. Thank you so much, sir. Thank you so much.
Sir, thank you once again to you and the chairman. Please convey my regards to him.
Yes, sir. I will convey, sir. Thank you, sir. Thank you so much.
Thank you, sir.
Thank you so much for your participation and your patience. So even though it was planned to be 1.5 hours, it has gone to 2 hours. So since the presentation went in an excellent way, so certainly this might have enhanced knowledge of different students, researchers, and faculty community. So thank you so much. And I would like to say, so please keep on visiting our chennai-technology.com/webinar or Chennai Technology in the social media like WhatsApp, Facebook, Instagram, and Twitter. Will help you to know more about the forthcoming webinars. And from 6/7/2020 to 10/7/2020, one program, there is one faculty development program has been planned by Mechanics Department. So those who want to register for the particular course, you can register. The registration process already has been started. It is available on the website, and it is on circulation. And this is not only for the faculty members of mechatronics, faculty from mechanical, electrical, electronics, and even computer science people also can attend the particular course. And not only faculty members, students can also go out of registration, since this will give a great knowledge enhancement, since the pupils are being called from eminent research institute and academic institutes. Okay. So as a new initiative, Mechanical Engineering Department of Chennai Technology has started a lecture series in mechanical behavior of materials. It's a very, very important one. This is being handled by Dr. V. Balasubramanian, who is one of the eminent researchers in welding and mechanical engineering of materials. He is known in national and international level. And those who want to go out of stations, even though the one class lecture was over by yesterday, and today the next lecture is between 4 to 5:30. This will go up to 6/7/2020. This will be a very good knowledge sharing. So those who want to register, you can go out for registration still. So we used to close one day ahead of the course starts. So because of so many requests, we are still opening the registration process for the lecture series on mechanical behavior of materials, because this is very, very important topic for mechanical, civil, and mechatronics candidates. And even the people, those who want to do research from physics also can participate. So it's not only for faculties, the students and the students also who want to enhance their knowledge can go out of registration to enhance their knowledge. And thank you so much. Thank you so much for your participations. So we will meet in tomorrow's webinar. Thank you.